We're getting started right away with a question right now. This is stuff that we worked on on Monday. So hopefully you've watched the Monday videos to catch up if you were not here. Let us see what the answer to this one is. It's not A. Wait. All right, let's work this one out. If I start with 0.460 moles of the compound, right? And I have 5 moles of ions. I'm going to have to get rid of this question. And per 1 mole of compound, because the answer is not here. That is right. So I end up with 2.3 moles of calcium 2 ions, and the answer is not here. This is what happens when I try to do things. I was actually looking for 1 mole. Here we go. All right. So first you must determine how many moles of hydrogen atoms there are in each compound. That's the first thing. And then you have to use the molar mass to see how many moles of each one there is. So the answer is B. For those of you who picked B, Mia, you had the right answer. You were thinking the right way, right? Doesn't it have to be half of the moles because of the mass? Yes. So can't be A because the formula is not correct. If we look at B, how many moles of hydrogen do we have? If I start with 9 grams times 1 mole divided by 18.02 grams gives me what? And I have 2 moles per molecule. That gives me 1 mole of hydrogen. Everybody see that? 9 divided by 18 is a half, times 2 gives me 1. C, what do I have? 17 grams is actually 1 mole of ammonia. So for every 1 mole, how many moles of hydrogen are there? 3, right? And for D, we have 24 grams of methane, and the molar mass of methane is 16 grams. So we end up with 6 moles of hydrogen. All right, so whenever you're given the mass and you want to know the number of moles of an atom, you have to multiply that mass times the molar mass and then the molar ratio of that atom that you're looking for. Okay? All right. All righty, now we're actually going to get into using balanced chemical equations to help us determine the amount of product that is formed or the amount of reactant that is required to end up with a certain amount of product. So remember, the law of conservation of mass has to be maintained, right? So if I start off with a certain amount of reactant, I have to end up with a certain amount of product. Now, will I have all of my reactant turned into product? Probably not, right? So there's always going to be a percentage that does not get converted into product. However, the total mass of my reactants must equal the total mass of my products. And because of this, we can use these molar ratios and the coefficients to help us determine how much reactant is needed to form a certain amount of product and how much reactant was used in order to get a certain amount of product. So notice that in this reaction here, we've got 3 moles of hydrogen reacting with 1 mole of nitrogen to give us 2 moles of ammonia. So from this information, we can determine that there are molar ratios, right? For every 3 moles of hydrogen that is used, how many moles of nitrogen must also be used? How many? I've got ones and twos. If I look at my formula, for every 3 moles of hydrogen that's used, I have to have 1 mole of nitrogen. And then for every 1 mole of nitrogen, how many moles of ammonia is going to be produced? What do we get? 2, right? So these molar ratios can help us determine how much product. So what do we get from a balanced equation? We can look at an equation in more than one way, right? Starting with 2 silver plus 1 sulfur gives us 1 silver sulfide. I can say that that 2 coefficient means 2 atoms of silver. Why? Because I have a solid, that means that it's pure, and we're talking about atoms. And it also means that I have 1 sulfur atom to form 1 formula unit, right? That has 2 silver atoms and 1 sulfur atom. What else does this mean? That means that if I have 200 grams of silver, I need 100 grams of sulfur to form 100 grams of silver sulfide, right? This also means that I have 2 times 6.0 times 10 to the 23 silver atoms, right? Which also means 2 moles, or 1 mole of sulfur to give me 1 mole. So how can we break that down even more? Well, the total mass, right, is going to be 2 times the molar mass of silver and 1 times the molar mass of sulfur to give me 1 times the molar mass of silver sulfide. So we get so much information from a balanced equation, and then that brings us back to the mass of reactants must equal the mass of our products, okay? So here we have an example of iron and sulfur coming together to make iron 3 sulfide. Now, one thing that we didn't really go over is that notice how iron, this is what iron looks like, this is what sulfur looks like, and we end up with something completely different, right? So when we have a chemical reaction, our products have a completely different set of physical and chemical products than our reactants. I just want to reiterate that again. So from this balanced chemical equation, we know that I have 2 moles of iron reacting with 3 moles of sulfur to give me 1 mole of iron 3 sulfide. And all of them are solid. Notice that those are the physical properties that we have. Each one of them is a solid. So what does this mean, right? It means that 2 moles of iron is going to react with 3 moles of sulfur, and I yield 1 mole of iron sulfide. So that's how I read this chemical reaction. 2 moles of iron reacts with, that's the plus sign, 3 moles of sulfur to yield, that's my arrow, 1 mole of iron 3 sulfide. So what we can get from this is our molar ratios. Let's do this question together. How can the following equation best be interpreted? Write your answer in the chat box. We can't just say what something reacts. We have to give the whole equation. Well, I guess we don't have the whole equation information, but. So our answer is A. How would we finish this sentence? 1 mole of nitrogen reacts with 3 moles of hydrogen to finish the sentence. To produce 2 moles of ammonia. Correct, right? So what can we get from our previous example of the iron plus sulfur to give us iron 3 sulfide. So I've got 3 different molar values here. And that means that I can have a molar ratio between each of the partners or each of the participants in this equation. So if I'm looking at iron and sulfur, I've got 2 moles of iron per 3 moles of sulfur. Same goes for 3 moles of sulfur per 2 moles of iron. If I'm looking at iron and iron 3 sulfide, there are 2 moles of iron for every 1 mole of iron 3 sulfide, and I can swap that equality. Once again, if I'm looking at sulfur and iron 3 sulfide, there are 3 moles of sulfur for every 1 mole of iron 3 sulfide that's produced, and I can switch this. So this is our, remember the other, for those of you who were here on Monday, somebody said that moles are the middleman, right? Moles are always the middleman, right? So you always have to get to moles, and you can only compare moles to moles. So if you're given a gram amount, you've got to convert that gram amount to a number of moles. And if I want to compare 2 separate substances, I can only compare moles, because 1 mole of every substance is going to equal the same thing, 6.02 times 10 to the 23 something, right? So that's why we have to compare moles to moles. So let's practice here. What is a mole-to-mole factor for this reaction? For number 1, a mole-to-mole factor between hydrogen and nitrogen is what? A, B, or C? All right, looks like the majority of you are saying B. Correct. What about a mole-to-mole factor between ammonia and hydrogen? For number 2. Hydrogen, not nitrogen. So once again, our answer is B. There are 2 moles of nitrogen for every 3 moles of hydrogen. Why is it not A? Because I have, if I look at the number of moles of hydrogen, I have 3 moles of hydrogen. And if I look at ammonia, I have 2 moles of ammonia. So it can't be 1 mole of hydrogen, it has to be 3. Okay. All right. Let's do a simple problem. Why is 2C? 2 was not C, 2 was B. 2 is B. Okay. All right. How many moles of iron can be formed from 6 moles of oxygen? All right. Well, before we get started, we have to think about what we're given. In this problem, we're going from the moles of one substance to the moles of another substance. Moles of A to moles of B, right? So if we look at our guide to doing these calculations, it says state the given and needed quantities, moles or grams. Step 2, write a plan to convert the given to the needed quantity, and then use coefficients to write mole-to-mole factors or write molar mass factors if needed, then set up your problem to give the amount, right? So what's our plan? First, our given amount is that we have 6 moles of oxygen, and we need moles of iron. So we're going from mole of A to mole of B, right? So in this step, we need a mole-to-mole conversion, which comes from our our balanced equation. So our mole to mole conversion is going to be 3:2, correct? However, so we have 3 moles of oxygen for every 2 moles of iron 3 oxide, right? So now we're going to use our mole to mole factor to determine our amount. So we are going to always start with what we're given, and then using that molar ratio, where I'm going to put the 3 moles of oxygen on the bottom and the 2 moles of iron on top, I'm going to end up with 4.0 moles of iron 3 oxide. So someone put 8 at the beginning, but it's actually half of that. All right. Why 4? Let's look at the math. If I start off with 6 moles of oxygen, that's my given amount, and I use my molar ratio between oxygen and iron, for every 3 moles of oxygen that is used, I have 2 moles of iron that are produced. So 6 times 2 is 12, divided by 3, and I get 4 moles of iron 2 oxide. Okay, so it's all about canceling out. So I cancel out my moles of oxygen, and I'm left with moles of iron. It would not have been the same if it was flipped, because remember, we always use conversions to cancel out the thing that we don't want, right? So if I put the iron 3 oxide on the bottom, I would not have been canceling out the correct molar amounts. So that's why we've been doing conversions from the very beginning, so that when we get to this part, we know that when we're writing a conversion factor, what we want to cancel goes on the bottom, what we want to keep stays on top. So I'm guessing that's how someone got 8, because they had the 3 on top and the 2 on the bottom. All right, let's try some more. In the chemical reaction of iron and sulfur, how many moles of sulfur are needed to react with 1.42 moles of iron? So we want to know moles of sulfur that we get from 1.4 moles, or that we need to react with 1.4 moles of iron. So this is, if I have 1.4 moles of iron, how much sulfur do I need in order for them to react completely, right? So my given is that should be a point in there, 1.42 moles of iron, and I need the number of moles of sulfur. So my plan is I'm going from moles of A to moles of B, right? So I'm going to start with what I'm given, 1.42 moles times 3 moles of sulfur divided by 2 moles of iron. Our moles of iron get canceled out. We're left with the moles of sulfur, and I get 2.13 moles of sulfur. Good job for those of you who are writing your answers in the chat box. Let's do another. Using the same equation above, calculate the number of moles of iron needed to react with 2.75 moles of sulfur. So our given amount is 2.75. What we need is our moles of iron. We're going from the moles of A to moles of B. So we start with what we're given, 2.75 moles of sulfur times 2 moles of iron divided by 3 moles of sulfur. Our moles of sulfur cancel out, and we end up with 1.83 moles of iron. What is the number of moles of iron needed to produce 8.2 moles of iron 3 sulfide? So it's the same type of problem, right? We're given 8.2 moles of iron 3 sulfide. We need the number of moles of iron. Same mole A to mole of B. So I'm gonna start off with 8.2 moles times 2 moles of iron, per 1 mole of iron 3 sulfide. Those cancel out, and I get 16.4. But this, we need to have how many sig figs? We need 2 sig figs, so we end up with 16 moles of iron. So those are the simple problems. Let's see. So let's work on this one together. How many moles of ammonia can be produced from 5 moles of hydrogen according to the following equation? You guys write how you solve this in the chat box. How do we solve this? Our answer is 3.33. We're given 5 moles and we need the number of moles of ammonia. So we start with 5 and our molar ratio is 2 to 3. 2 to 3 ammonia per 2 ammonia per 3 hydrogens, and we get 3.33 moles of ammonia. Good job. Here we go back to our challenge question, folks. And let's see what our answer is. The answer is D. If we were to write true statements, a true statement for number 2 is that 4 moles of hydrogen atoms is equal to 2.4 times 10 to the 24 atoms, right? Because we actually have 4 moles of hydrogen atoms for every 1 mole of methane. So we would need 2.4 times 10 to the 24 atoms. If we were to look at number 4, 2 moles of methane would produce 2 moles of carbon dioxide, right? Because it's a 1-to-1 ratio. And number 5, a true statement would be that liquid water is produced. So let's look at, so 1 is correct because there are 4 moles of hydrogen for every 1 mole of methane. Let's look at the formula. 1 carbon, 4 hydrogens. So that's 4 moles of hydrogen for every 1 mole of carbon that is in methane. Number 3 is correct because in 18.02 grams of water, that's 1 mole. So for every 1 mole of water, there's also 1 mole of hydrogen atoms. What about how many moles of hydrogen are there in 1 mole or 18.02 grams of water? Correct, 2 moles, all right?